Electrochemistry is the study of changes between chemical and electrical energy. And if we need to sum things up, the idea is electrons are moving. So there's some type of electron transfer. And in the big picture, our goal is to use that electron transfer to do work. In short term, the electrons just move from one place to the other. But if we can separate them, we can harness that energy as the electrons move from one side to the other, and we can make them do work to get from one place to the other place. There's two basic ways that we look at electron transfer for electrochemistry, oxidation-reduction chemistry, one of which is we have electrons moving in a spontaneous direction, all right? It's energetically favorable. The Gibbs free energy is negative. So we have electrons move in a spontaneous direction. And when we do that, their movement generates electricity. All right? So spontaneous electron movement to generate electricity. And then the opposite is also true, and that is using electricity to force a reaction in a non-spontaneous direction. Right? So you can use electricity to force electrons in a non-spontaneous direction. Right, and that is forcing a reaction. And when we say non-spontaneous, we don't mean that the reaction doesn't happen. We just mean that numerically or energetically, the reaction doesn't happen in the written direction from A to B, but it would happen in the opposite direction from B to A. And that's not super important terminology for right now. We'll have galvanic cells and voltaic cells, and we'll do those calculations. But I want to take a look at some examples of where this is taking place in our day-to-day lives. The obvious example is batteries, and I guess I'll look more at that later. But I think for household implements, one of the classic examples is the gutters around your house. Most of the time, gutters are made out of aluminum, and people don't realize it, but you can't use iron nails with aluminum because your gutters would oxidize. They would act as a sacrificial anode, and the gutters would just fall down. So we might say when iron is exposed to water, it would rust. But in a case like this, when the iron is exposed to water in the presence of the aluminum is more reactive. It oxidizes first. So the aluminum rots away to protect that iron nail, and then the gutters fall down. So I think that's a pretty common example that people don't think about. Other things would be like an iron buoy out in the ocean. So they have these things to mark locations in the ocean where ships need to go, and those are made out of iron. And over time, that iron actually wouldn't take much time for that iron to oxidize away. So they'll strap in there literally a big chunk of something like zinc, and then that zinc will oxidize. It's a higher energy species, and so instead of the iron rusting away, the zinc will oxidize. It's called a sacrificial anode. And those periodically have to be replaced. They're getting used up over time. If you look back, or if you talk to your parents or grandparents, fillings didn't used to be epoxy composites or anything like that. They would literally grind out your tooth and put silver in there. And it was an interesting thing that was rather uncomfortable if you happened to get a piece of aluminum foil in your mouth, which sounds kind of weird, but like if you had a stick of gum with the wrapper sticking to it, it would give you a very uncomfortable sensation as an electrochemical reaction would be taking place right on the nerves of your tooth. So that would be another more simple example. And the idea with this electrical and chemical energy transfer is potential energy, and I think it's very important to look at that in a simplistic way of potential versus kinetic energy. When we talk about in physics the idea of potential energy, stored energy, and kinetic energy, the energy of motion, a classic example would be like you have some mountain or whatever, and you can apply a force to some object, we'll just say a boulder. Force applied over a distance is work, and then the object might appear at the top of the mountain, and it has stored energy. It is possible then for the boulder to spontaneously roll down, And as it does that, it is releasing that energy in the form of kinetic energy, right? So as the ball goes down, it happens like that. And I think with electricity, it's important to look at it in terms of the vocabulary we have, which is we talk about electric current, which is a measure of the flow of electrons. And instead of looking at this with a ball moving up and down a hill, we can look at it as maybe a stream flowing. And then you've probably seen in movies or whatever some type of grain mill, and we're stuck with my caveman drawings here, but there's some water wheel that turns as the water flows by. So as there's this flow of water from some higher area to some lower area, this wheel turns, and it might be used to grind grain or generate electricity or something like that. And that's the water moving in a spontaneous direction. And that's the idea very often with hydroelectric dams and things like that that we use today. So instead of talking about water or boulders rolling down hills, we have lower energy states for chemical species, and we have higher energy states. And as those electrons move, there is a flow of electrons, this electricity, due to an electromotive force. And that's where we can get our work done, by that electricity. All right. So with that in mind, and with those examples in mind, it's important to look at what actually happens in a redox reaction. So in a different video, I talk more about oxidation-reduction reactions. Right? And so oxidation, we have an increase in oxidation state, which is essentially the charge, and I go more into that vocabulary in a different video. And then reduction, we have a decrease in some oxidation state. And a very, very simple example, if we were to make one up, is if we have like our iron nail situation, where we maybe have aluminum gutters, and then the water comes along, and it would take some iron and start to turn it into iron ions, and let's just say we have iron 2+. This happens to be more reactive, a higher energy state, and we can judge that from a table, the electromotive series, or we can look at it qualitatively with the activity series for single replacement reactions. But in this case, it's favorable for the aluminum to lose those electrons instead of the iron. And so the aluminum will donate those electrons to iron. There's an energetic favorability to that. So you end up with the aluminum oxidized and the iron in its reduced state. And literally, that's our terminology. Aluminum goes from a 0 in its elemental state to a 3+, so the aluminum is oxidized, right? Which makes it, as we look at this terminology again, the reducing agent. All right? And the iron goes from a 2 to a 0, so the iron ions are reduced, which makes it the oxidizing agent. All right, and the terminology is pretty straightforward. That was a 2, that's a 0. It went down, it was reduced. How did it get reduced? And the answer is there's some transfer of electrons here. This gives up electrons, this uses those electrons, and that's the basis of redox or oxidation-reduction reactions, is the transfer of electrons, causing something to go up in oxidation state and causing something to go down in oxidation state. Now, a reaction like this is pretty straightforward visually. It's not balanced as we see it, and that's something you probably don't think about is, well, I've got an aluminum, and I've got an iron and an iron. Where it's not balanced is charge, and that's where redox gets a little more complicated. If we wrote this out as a single replacement reaction, we might have aluminum and iron 2 chloride or something turning into aluminum chloride and iron, right? So instead of having those charges, we might put in some spectator ion. And the catch is, anybody could look at this and set up a little table of reactants and products and say we've got aluminum and iron and chlorine, 1, 1, 2, and on the product side we've got 1, 1, and 3. It's not balanced, all right? And then we could do our brute force balancing with the table and say, all right, I need our aluminums to match. We'll end up putting a 2 there and a 3 there and a 2 there and a 3 there, and we end up with 2 aluminums and 3 irons. and 6 chlorines. All right. Looking at this, you wouldn't expect any balancing at all, right? 1 aluminum, 1 aluminum, 1 iron, 1 iron. So a mass balance isn't enough. There also has to be a charge balance. And I think that's not the intuitive thing at all. And it's going to lead to the bigger picture of redox balancing. And we'll break reactions in half to take care of that. So a quick note here, if we look at this side, 0 is our charge and 2 plus is our charge, right? So this side happens to have a 2 plus charge. On this side, we have a 3 plus charge and a 0. We end up with a 3 plus. And we see this relationship of a 6. A quick sketch of how we deal with this for a simple reaction, ignoring the spectators, is we break it into half reactions, something being oxidized and something being reduced. I've got aluminum turning into aluminum 3 plus, and I've got iron 2 plus turning into plain old iron 0. To make this happen, the thing that's missing is 2, or in this case, 3 electrons. And down here, we've got to have 2 electrons to make this happen. So the overshadowing idea with electrochemistry, something has to give up electrons. They have to supply electrons, and that is the reducing agent, because those electrons go somewhere else and reduce it. So this supplies electrons, and this uses electrons, and for the overall reaction, we need that number of electrons to match, all right? Because one is providing them for the other one. So what we end up doing in redox is trying to get those electrons to match. That's 3, that's 2, least common multiple is 6. So we put a 3 there. We end up with, again, 3 of our iron ions and 3 of our iron atoms, 2 of our aluminum atoms, and 2 of our aluminum chloride, all right? And the chlorine just acts as a spectator to balance charge. Now we're going to have to take a much closer look at this. In order to do that, we're going to have to practice assigning oxidation numbers, which is what we'll look at in the next video. We'll look at oxidation-reduction, half reaction, and balancing like we did here. And then we'll take a look at some applications of that.